Hi, this is today's lesson on scientific notation. And so if you're not familiar with scientific notation, it is a way to write very large numbers or very, very small numbers um, without 0, 0, 0, like all those zeros. And so the number 3,400,000,000 would be the same as 3.4 times 10 to the ninth power. So positive exponents on the 10, very large numbers, negative exponents on the 10, very small numbers. The general structure is to be in scientific notation, the decimal number has to be between 1 and 10. You could have other things that are equivalent, but they would not be in scientific notation. So if you want to change from standard form, our normal numbers, to scientific notation, oh, and it's always times some power of 10. So you'll have to move the decimal point as much as needed to get the decimal number between 1 and 10. So if I had 3,562, I would want to place the decimal. Remember, the decimal is at the very end of the number because that would be the same as 0.0. Don't have to add the 0, just trying to show you that that's where the decimal place is. And then we would need to change that to 3.562 or 3 and 562 thousandths. So how many places did we have to move it? We moved it 3 places. So to make that number equivalent to the original number in standard form, we would need to multiply it by 10 3 times. Each time moves the decimal 1 place to the right. So that would be 3.562 times 10 to the third power in scientific notation. If you have to move the decimal left to place it in the right place, the exponent on the 10 is going to be positive. If you had to move the decimal to the right to make it a number between 1 and 10, which means it's actually a very small number, the decimal will be negative. So keep in mind that left and right business is about when you are moving it from standard to put it in scientific notation. So we have a few more here to practice. And so let's see. So here we have the decimal is going to go between the 8 and the 5. There'll just be one place to the left of the decimal. So notice the numbers are not changing. 8546, 8546. But I move the decimal from here at the end, 1, 2, 3 places. So to make that back to that original number, I would need to multiply times 10 to the third power. So 23,000, I think originally I had a comma in there that for some reason did not print. So this would be 2.3 times 10 to the 1, 2, 3, fourth power. Sorry about that. There we go. Fourth power. So 572 and 9/10. 5.729. 10 to the second power. Now, some of these aren't really huge numbers, so it might seem like, well, this is actually looks longer than just writing the number. But we're just getting used to it. So again, these are gapped out to be able to include commas. So this would be 2, and then our decimal 9, 9 times 10 to the 3, 6, sixth power. Those nice little sections are making it easy to count by threes. So you may have seen scientific notation come up on, say, a calculator. If the number you put in was either super big or super small and couldn't fit on the screen. So we've got a few more here. We've got a few that we will get into that have negative exponents. So if you want to pause and try these and see what you get. So only one place to the left of the decimal. 4, 1, 8, 0, 0, 6. That is an 8 over there. And that would be times 10 to the third. Think about, you'd have to move it 3 places to the right to get it back to normal. So now we have our first one that is a small number. So I need it to be over here. So to get it over there, I'm moving it 1, 2, 3, 4 places. So this is negative fourth power. Because to actually make it back to its original form, we would be dividing by 10 4 times. So number 7, 6, decimal, 5, 7, 4, 3, 10 to the negative, only negative 1. I only need to move it 1 place. So here, 2.24. And this would be negative 2. 1, 2 places. So if we want to go from scientific notation to standard form, we're moving the decimal to the right. We're going to move it the number of places of the exponent. So if it's a positive exponent, we're going to move it to the right. If it's because that's repeatedly multiplying by 10. If it's a negative exponent, we're going to move it to the left. So that. And if there are not enough places, then we must add zeros. So this would be 2,000. Okay, that's not better. Actually, let's try this. So this would be 2, 3, 3, 1. Now that's moved 1, 2, 3 times, 2 zeros. And then I could go back and place a comma to make it easier to read. So it went 1, 2, 3, 4, 5. So I got 2 spots. That's why I had to add 2 zeros. So this one's going to come back the other way. We're going to be going from here. It's just a whole number. It's understood to be to the right. 1, 2, 3. So there are 2 places here that need zeros. So 0.005 Or we can write 0 in the ones place and 0.005. The 0 in the ones place is negotiable. It's, if I say 0 and this, or I just say, so you'll often see it, but it would have the same meaning without the one on the left, but you need both those zeros to the right of the decimal before the 5. So here, I need to move it 5 places to the left. It doesn't matter that we already have 3 places to the right. We still have to move it 5 places to the left. So it's going to use up one of those places to jump over the 7. And then we still need 4 zeros after the decimal point. So 0.1234 zeros, 7627. Here. And number 5, 10 to the 3rd. So we're going to move it 3 places to the right. Positive exponent, so 3 places to the right. And there are actually 3 decimal places. So all that does is move across those. And if you wanted to write the decimal, it would be right there. So since it's just a whole number with nothing to the right, I don't have to write the decimal, but up here in number 2, you could also put a decimal at the end. Number 7 would be 506 and 2/10, so it's just moving 2 places to the right. So when we multiply and divide with scientific notation, this is going to be how we're going to handle really big numbers instead of putting a ton of zeros in our calculator. We can think about what we did with our product rule and quotient rule with variables. So we're going to multiply. It's like the one number between 1 and 10 is kind of like the coefficient. You're going to multiply those numbers and you're going to add the exponents. And then you're going to have an adjustment step if the multiply answer, the product, is not a number between 1 and 10. Same thing for division. We're going to use quotient rule. We'll divide those numbers that are between 1 and 10. And then we'll subtract the exponents. So, for instance, here, they're telling us what happens if it's not incorrect scientific notation. So if I get 17 is equal 17 times 10 to the 10th, well, 17 is not a number between 1 and 10. 17 is the same as 1.7 times 10. So that extra power of 10 gets added on to the 10 to the 10th to make 10 to the 11th. And the same thing if it's too small, like 0.15 is too small, then we have to take away 1. There should be a -1. Oh, this says times 10. Okay, so to make it 1.5, it would have to be, we have to take one of our powers away. We have to use up one of those powers. That's why they've broken this down as a 10 and a 10 to the 5th. That's how it became 10 to the 5th. So if it's too small, you'll take 1 off your exponent. If it's too big, you'll add 1 to your exponent. So you're going to fill in this chart and kind of follow the pattern here. Also, if you look at the place value chart that I gave you, that may be helpful also. So we see that, for instance, trillion is 10 to the 12th, billion is 10 to the 9th. So when we think about these powers of 10, and we already looked at some of what's going to come on here, coming up, because I had created that other sheet. But there is a new name for every 3 powers of 10. Or I guess I should say every 3rd power. For every 3rd power of 10. So we had thousands, and we had millions and billions and trillions and quadrillions, and then quintillions, sextillions, septillions, etc. Okay. So those are called periods, and then that's when we're writing those commas to help us read it more easily. The relationship between that 2nd and 3rd column above is that the number of zeros in standard form is the power of 10. So for instance, if it is 1 million, a million has 6 zeros, and it is 10 to the 6th power. And this number could be said either way, 1200 or 1200. Either way is acceptable. And then this just gives us what we practiced quickly on the other page. So if I want to write these in scientific notation, so remember a number between 1 and 10, so 3.257 times 10. I don't have a good way to type power. So for power, I'm going to do this to show you that that's my exponent. So that would be 3,678. So the 8th power. And remember, I got that from, this is where the decimal is. So here's 3. 3 more makes 6, 7, 8. Or like, if I'm going to put it here between the 3 and the 2, how many places would I have to move it to the right to get it back to normal? 8 places. So if you have something like this with the word, don't add a bunch of zeros first. Just think about the chart. Billion is 10 to the 9th. So I can just say 7.3 times 10 to the 9th. Now, if I'm supposed to write it in scientific notation and I have the word million, right? I have the word million, but 92 is not a number between 1 and 10. So think about what you would do with the 92. You would have 9.296 times 10, which would be 10 to the 1st, times 10 to the 6th for the million. So then final answer, which you might be able to do this in your head without needing to write some steps, but 10 to the 7th. So we have 6, 10 to the 6 for the million, and one more 10 to change the 92 to 9.2. So here I need this to be 8.6, but that would be 8.6 times 10 to the negative first, and then million, so times 10 to the 6th. Now I'm going to add -1 and 6, so this will equal 8.6 times 10 to the 5th, because it's 1 less than the million. So you may just be able to think that 1 less, because my decimal is not between the 8 and the 6, it's too small, so I'm going to take 1 off the 6 and make it a 5. With a little practice, that becomes pretty second nature to do. Sorry. To be honest, because primarily what you're doing is counting or moving the decimal, I don't find a calculator to be too helpful, because you're always running the risk. You still have to count the zeros and type things in and things like that. I mean, you certainly can, but I think it's probably riskier to use the calculator than to not. So we need to move it 5 places to the right, since it's 10 to the 5th. So 6, 7, 8, 9, 7, 8, 9, that was 3 places. Add 2 zeros. And then I'm just going to insert a comma to make it easier to read. So here, times 10 to the 3rd, so 3 was already to the left, 1 place, 2 place, 3 places, decimal, 7, 8. So I moved it 3 places to the right. And then down here, we would first want to do the 5.92 times 6.3. Now, this gives me 37.296. But we have something called significant digits. And so if 3 was the most significant digits we had in either, like we have 5.92, all right, then that's the most significant digits that we can have. So we're going to only keep 1 decimal place after the decimal. So this is going to be 37.3 times 10. Add the exponents. 9 plus 5 is 14. And then adjust. So then that's going to be 3.73 times 10 to the 15th. So sometimes we've got to do that adjustment. So over here, usually see this in fraction form for division, but it wouldn't have to be. 1.9 divided by 4.62. Again, this really gives me lots of decimal places, but because 4.62, 3 significant digits, so I'm only going to keep 3 digits. So 0.411. And at this point, I'm not going to try to do 2 steps at once. I'm just going to do that times 10 to the, subtract the exponent, so 10 to the 9th. And then now we're going to adjust. It's too small. And move the decimal over. Since it was too small, I take 1 off my power. I used up 1 power of 10 to change the 411 thousandths to 4 11 hundredths. Sorry, guys. I'm doing a lot of fast forwarding through my fumbling around here. So some applications of this. Instead of doing 31 and 9 zeros, right? We can use scientific notation to do the calculations and then convert to standard notation to express our answer. So here we go. I'll use this. Try this. So 31 billion would be 3.1 times 10 to the billion 9th power plus 1 more, because I had to change 31 to 3.1. So that's the budget. If it's dispersed among 292 school districts. So we're going to divide by, and we can do 2.92 times 10. 292 is not really that huge of a number. If I was actually not saying like, make sure that I have this in scientific notation. Oh, that's not right. 2. Just 2. I wouldn't necessarily have to change both. So in this case, I just went ahead and changed them both. So now I'm going to do 3.1 divided by 2.92. I'm only going to keep 3 numbers. Those are my significant digits. So I have 1.0616. So 1.06 times 10 to the, we're dividing, so we subtract 8th. So how much money will each school district receive? Each school district in Indiana. Well, obviously, all school districts are not going to receive the same amount, so I'm going to say an average of. So if I put my 8 zeros back in, right? Or I think about, what does 8 zeros tell me? $106 million. So how did I get 106 million? Well, if I move it over 2 places, that's the 106, and 10 to the 6th is million. So $106 million. Is that an exact number? No, it's not an exact number because we didn't figure it out down to the cent, right? So in number 2, we have 2.2 million Americans incarcerated. It costs $25,000 to house an inmate for a year. How much is the US spending on incarcerations yearly? So this time, 2.2 million, this is an easy one to put in scientific notation, 2.2 times 10 to the 6th. Now we're multiplying. So this times 25,000 would be 2.5 times 10 to the 1, 2, 3, 4. 3 places for the zeros, or 1 more place. So we multiply this, we get 5.5 times 10 to the 10th. Think about the closest period. So in the earlier one, the smallest, the period below this, I guess. So 10, so 9 would be billions. So that gives me the 1 extra. So then I could say US is spending approximately $55 billion a year on incarceration. So one of the 10s got used to make 5.5 55, and the other 9 are included in the word billion. All right, let's do a couple more and then I'm calling it a night. This is kind of disgusting to think about, but it is estimated that a single droplet from a sneeze can contain as many as 200 million germs. And if a sneeze is composed of 40,000 of these droplets, how many germs are in a single sneeze? Right. So first we need to think about, is this one, we're going to do scientific notation. That's kind of the lesson. But we also need to decide if we are multiplying or dividing. So each droplet's this, has this many, there are this many droplets. Yeah, we're multiplying again. So 200 million would be the same as 2 times 10 to the 2 zeros plus 6 for million makes 2 to the 10 to the 8th, sorry, times the 40,000 droplets would be 4 times 10 to the 4th power. So when we multiply those, this is a nice easy one. 2 times 4 is 8 times 10 to the 8 and 4 is 12. So 8 times 10 to the 12th. So that made it easier to work with than a whole bunch of zeros. Now we need to translate that, write our meaningful sentence. So there are about million, billion, trillion, right? Wow. 8 trillion germs in a single sneeze. That's a lot of germs. A lot of germs. Okay, Lucas Oil Stadium holds approximately 70,000 spectators. So how many stadiums would it take to hold the entire US population? So you'd want to go back to number 1 on the previous page and do that number. I want to say it was 321,000. So pretend with me it was, or 321 million, my bad. Only, times 10 to the 6th. And if that's not the right number, then at least it's the right process. So that would be nope, this would be 10 to the 8th. That would have only been 3.21 million. That would be 321 million. And we're going to divide that by how many we can put in one stadium, which is 70,000, which is 7 times 10 to the 4th. And it would be appropriate to round this to a whole number of stadiums. And number 5, we're going to look at and see about divvying up lottery winnings. I'm going to leave this sit here. I'm just going to get these last couple set up. Sorry, I have to get rid of this to be able to move my cursor. Okay, now this time we have 1.3 billion. So 1.3 times 10 to the 9th power. And if we split that up, divvied it up among everyone in the country, if we just, and this is just saying the meme estimated the population to be 300 million. So that would be divided by 3 times 10 to the 8th power, okay? Because 3 million would be 6th power, 2 more zeros, so 8th power. So 1.3 divided by 3 gives me 2.433. 3's forever and ever. And this would be times 10 to the, subtract those exponents. So 10 to the 1st, which would be $4.33. So 1.3 billion. And there are 300 million people. So think if I multiplied 300 million times 4, I would be at 1 billion at 200 million. So like 1.2 billion. So what does this mean? This means if the lottery jackpot of 1.3 billion was divided among the population, each person would receive $4.33. Don't spend that all in one place. All right, I hope this was helpful. There are some, I don't think there's a official like assignment looking page. And so in class, we will have worked through several of these things together, and then I'll be kind of turning you loose. Toward the end here, I think we have some other things, but I'll make another video about per capita because we're still going to use some things where scientific notation or the fact, as we already know, if they both say million, we can just get rid of that, but save per capita for a different video. Thanks.